All right, so earlier we talked about how to find the volume if we took a portion of a graph like y equals x squared and revolved it around the y-axis. So here we're going to talk about the surface area, the outside surface area. If you take this parabola, spin it around the y-axis to generate a bowl-looking shape, we want the outside surface area. If you were going to paint the outside of the bowl, what would that area be? Okay, so the idea, just like always, we're going to consider a small cross-section slice, horizontal slice of this bowl. And this time we're not interested in the volume, we're interested in the surface area around this. So think of this as a thin band. I like to think of this as if you slice an orange, like part of an orange, you're looking for the area of the peel around it, okay? We don't care about the volume. Now, it turns out for the area, we're not going to think of this as like when we do volume, we can think of this as a disk with vertical sides right here. We actually want to preserve the curvature of the graph for our thin slice. This is not straight up and down. This actually has a curve on the ends here. Now, if you cut this little strip surrounding this disk and straighten it out, it is going to resemble a rectangle where the length of it is the circumference of the circular disk, and we know the circumference formula is 2 pi times the radius. But instead of using like the height like we do with the disk method, since we're preserving the curvature, this length is a small piece of arc length, right? That's a small piece of arc length of the parabola. We covered that in the previous video, and so we're going to call that ds. That's an infinitely small arc length. Nevertheless, it does resemble a rectangle, and so the formula for the surface area of that thin slice there is 2 pi r times ds. Now recall the formula for ds, we have a couple of them. Most of the time, if your function is written in terms of x, ds is the square root of 1 plus dy dx squared. And the radius in this case, if you're revolving around the y-axis, the radius of this slice is the distance from the y-axis to our random point. Remember, this is an arbitrary slice, and that would be x. That's just a random x value. So our radius is going to turn into x. There's our formula for dx. 2 pi is a constant, so we can pull that out. The derivative of x squared is 2x. We have to square it, so that gives me 4x squared. Put that in there. And we were given in the problem, x went from 0 to 2. And here's a good example, a good time to use u substitution. If you let u equal the inside of the square root, 1 plus 4x squared, my du will be 8x dx. I can, remember the wishing technique, I have an x dx, so I can wish for the 8. I should probably put that there. Wish for the 8. Compensate with a 1/8 outside. So the 8x dx gets traded in for du. The 1/8 will stay there. And I'm choosing again to not convert the limits. You can if you want. I'm going to integrate this with respect to u, 2/3 u to the 3/2. Plug my u back in, 1 plus 4x squared. Simplified 2 pi over 8 simplifies to pi over 4. I took out the 2/3 times pi over 4 is pi over 6. And then if you just plug in the 2 minus what you get when you plug in the 1, there's our final answer. Let's do another example. Oh yeah, with surface area, so what if we took that same shape, y equals x squared, and revolve it around the x-axis? Same formula, 2 pi times the radius times ds. My radius now would be y, right? That's a y distance. And you can use, since y is equal to x squared, you can use x squared as your radius. And then we had this for ds before on the previous problem. And sometimes this will happen. We can find the surface area when it's revolved around the y-axis, but when we try to revolve it around the x-axis, we end up with an integral that at this point we can't do. Think about the u substitution. If you tried to let u equal 1 plus 4x squared, du would be 8x. And we do have an x, but we have an extra x. And there is that idea of solving for x in terms of u. It's not going to work out so well on this one. You can try it if you want. So I just want to make a note. Sometimes you won't be able to do the integral. We will find a method to do this integral later on in the course. Okay. All right. Here's one. We're going to take a portion of y equals the square root of 2x minus x squared. I should say that's the actual whole graph there. That has intercepts at 0 and 2. Kind of resembles a half of a circle. Anyhow, we're going to revolve that around the x-axis. I know that I'm going to need to do dy dx and then square it, and I can tell that's going to take a little time, so I usually do that first. So the derivative of that function is 1/2 stuff to the negative 1/2 times the derivative of the inside. Simplify it, so this can now go to the bottom because it's to a negative power with the 2, and this can slide over to the top. And if I factor out a 2 from the numerator, I can cancel that out. So I'm left with 1 minus x over the square root of 2x minus x squared. And if I square that, I'll just square the top and it'll get rid of the square root in the denominator. Okay. Since we are revolving around the x-axis this time, we can make our radius would be y. The radius of that disk is a certain y value. And so I can use my function for y, 1 plus dy dx squared. So to find this antiderivative, what we can do is let's do a common denominator. So if you multiply this 1 top and bottom by 2x minus x squared, you actually get some stuff canceling out. And you have to expand 1 minus x squared. I expanded that right here. Some stuff cancels out, leaving me with just 1 over 2x minus x squared in the square root, and then the square root out here. Now, if you break up that square root as just 1 over the square root of 2x minus x squared, that cancels out. So we're just left with 1. All of that simplifies to 1. The antiderivative of 1 with respect to x is just x. So you plug in from 2 to 0, and we get an answer of 4 pi for our surface area. All right. When we were doing volume, we derived the formula for the volume of a sphere. And there's also a formula for the surface area of a sphere. Some of you may know that, but if you don't know it, here's a way you can derive it. A sphere, once again, is just formed by taking the top half of a circle. I have it as my radius is a, so it'd be the square root of a squared minus x squared. Rotate it around the x-axis, and I'm going to use my surface area formula. The derivative is 1/2 stuff to the negative 1/2 times the derivative of the inside. Remember, a is a constant, so it would just be negative 2x. The 2 cancels with the 1/2. I'm going to take this negative x, put it on top, and bring this down to the denominator. Then it's easy to see when I square dy dx, it's just going to be x squared over a squared minus x squared. My general formula for surface area, 2 pi times the radius of one of my cross sections times ds. The radius would be y, which is the square root of a squared minus x squared. And we already worked out dy dx squared, so it'd be 1 plus x squared over a squared minus x squared. Similar technique to the previous problem. If you do a common denominator, if you multiply this 1 top and bottom by a squared minus x squared, you're going to get a squared minus x squared plus x squared. Those cancel out over a squared minus x squared. And if you break this up into two separate roots, the square root of a squared over the square root of a squared minus x squared, these guys cancel. Because a is a positive number, it's the radius, the square root of a squared is just a, which I pulled out. And notice that once again, that just leaves 1 to integrate. And the antiderivative of 1 is just going to be x. If I plug in from x equals a to x equals negative a, that gives us the maybe familiar formula for surface area. It's 4 pi times a squared. 4 pi times the radius squared is the surface area of a sphere. So kind of cool. Back when you learned that formula, perhaps in a geometry class, I'll bet a teacher never really was able to give you a good explanation for why the surface area formula was 4 pi a squared. And that's because I really think using calculus is the best way to derive that formula, and the only way I know. Now, there's an interesting side note with this particular question, which is kind of fun to think about. Suppose this sphere was a loaf of bread. Some people like bread. I definitely like bread. And a lot of times it comes in the form of like a hemisphere. You may see like where it's a top here and then round on the bottom, not a full sphere. And I know in my house, when we slice up fresh bread, we always have an argument over who gets the crust piece, right? A lot of people like the chewy crust on the fresh loaf of bread. So here's an interesting question. Imagine this was a loaf of bread and these were all even slices. So maybe here's a slice of bread here, right? And you've got a bunch of slices throughout here. One interesting question is, if you sliced up this loaf of bread into equal widths, which piece or pieces would you think has the most crust on it? And of course, a intuitive answer would be the end piece, right? If you slice this piece right here, it's all crust right here on this side, and that's the piece usually most people in my family go for, because it's all the crust right on the end there. Okay, but an interesting thing is that it actually doesn't matter which piece. If your loaf of bread is in the shape of a sphere, all the pieces actually have the same amount of crust. And you can kind of tell that here when we got to this part of the integral and everybody just canceled out, just left us with a 1 here. Imagine you were doing the crust, you were finding the surface area of the crust between x equals 1 and x equals 2. You would get the same answer as the area of the crust between x equals 3 and x equals 4, if you think about it, right? Because you're going to just be plugging in either 2 minus 1 will give you 1 there, or if you go 4 minus 3, you're going to get 1 there. It's going to give you the same answer. So very interesting. If you now, if you ever have arguments in your family about who gets the piece with the most crust, you can settle the argument by telling them all of the slices have the same amount of crust, so it doesn't matter which piece you choose. Okay.